Hello, everyone. Welcome back. So we are looking at the exam paper for 2015 to 2016, the second question. So first of all, this one looks a little bit complicated, but it's actually really easy because everything's ready for you. So basically, you have SDMA, you have two users, and then experience feeding channel, and then at the receiver you have two receiver antennas, and during two time slots you receive all these signals. So the receive signal model can be written in this form. So the first question is you need to extend the expression for y11 and the y21. And then eventually you want to arrive here. So because the transmission pattern has repetitions, you have x21, for example, transmitted twice with some change in conjugate. So this is repeated information. And then we want an equivalent model that only have what you transmitted without repetitions. So what do we do? It's actually really easy because everything's already written out for you. So if we look at y11, based on this model, it is the first row of x1 multiply the first column of h1, and then plus the first row of x1 multiply the first column of h2. So you can check that if you want to get y11, it is the first row multiply the column vector. So you should get the same result. And then y21 is slightly different. So I have y21 here, which is a second row and the first column. So you have the second row of x1 multiply the first column, and then the second row multiply the first column. And then for y21, we need to take conjugate y because we want the transmission vector to be in the same form as the first one. So you see here that the signal here has conjugate, but as a receiver, you cannot change what has been transmitted, but you can conjugate on the received signal. So that is the equivalent model would have of this one, multiply this one, would have the same form for the transmitted signal without any conjugate. So that was a 10 mark, but it's actually really easy. And then the second question is also super easy because actually all the tips you need are already written out here for you. So based on this H, it's read the first column is H1, second column is H2, third column is H3, and then H4. So now you need a single user decorrelation. And you have the decision variables here. And what we want to show is that there's no interference between x1 and x2. So there is basically no interference between the two antennas within a block, but there will be interference between blocks. So here, if you extend this by H1, H2, sorry, let me try again. So if you extend, you need to extend this by H 1 H, H2 H, H3 H, H4 H. This multiplies H1 H2 H3 H4 in Y. Okay, so check again. So that 1, the first decision variable is this one multiply this one, and then say 1, first one, first column. Then you have x1, x2, x3, x4. So Z11 is this one multiply this one with x1, and then x1 Hermitian transpose multiply h2, and then multiply x2, and then h1 multiply h3 multiply x3. Okay, so we need to show that there is no interference between the what we need to show is h1 h multiply h1 x1, and the second term plus h1 h2 x2, and then you have the third term h1 h3 x3, and then you have the fourth term h1 h4 multiply x4. So all of these give you Z11. So what you need to show is this one equals 0, so that there's no interference. And this one only has power. So basically, if you look at the first column, so if first column multiplies the second column's conjugate, you'll get 0. I'll leave this to you to do the extension. So basically, if you check that on paper, you'll see that the first column's conjugate multiply second column, then you get a 0 for this one. And then the first column's conjugate multiply its own the column, then you get all the powers without any phase rotations. So so if you just expand the equation, then you'll see that there's no interference between x1 and x2. And also the second, you need to show that what are the interference terms. So h1 multiply h3, and then h1 multiply h4. These are all interference terms. And then you need to state which complex multiplication gains must be estimated by the receiver in order to perform a single user detection by the first user. So for Z1, we actually only used H1. For Z2, we will only use H2, the knowledge of H2. So for the first user, you only need to know the channel of the first user. right? But you still have the interference here. So the next step is you need to apply multi-user detection to completely cancel out the interference. And then you need to state which of channel gains must be known by the receiver in order to cancel the interference. So basically, you have the previous step has Z equals H, Y. In order to completely cancel interference, what you need to do is you need to do the matrix inverse. And then the matrix conjugate, and then receive signal. Then in this way, the effect of fading is completely cancelled because there is H in Y, right? So this is completely cancelled. So all of this need to know the whole fading matrix. So you need to know the fading gain of all the users. So this question is actually quite simple compared to coursework because everything you need for the equations are already presented in here. Okay, so let's that was the second exam paper. Let's look at the third. The third exam paper. So this is the exam paper for the year of 2016 to 2017. Okay, channel modeling. So now you have two equations shown to you here. What we need you to do is you need to tell me what are they? So these are the two models for path laws. You need to tell me what they are and what their parameters mean. What are the parameters meaning? Okay. So the first one is mostly about the distance. This is a free space path laws, which indicate power decays with signal power decays with respect to distance. It should on page 15, I think. Page 15 here. So this is here free space path laws. So power decays with the second power of the distance. So for that question, A should be 2, right? Second power of the distance. And then the second path loss model is ground reflection model here, which describe how power decays with the fourth power of the distance. So B equals 4. And then you need to explain all the parameters. So GT is the antenna gain as a transmitter, GR is the antenna gain as a receiver, C is speed of light, this is carrier frequency, this is the distance between transmitter and receiver, this is the height of base station, height of mobile station. They're all quite basic. Secondly, explain the coherent bandwidth and coherent time of various channel. In each case, describe the related physical phenomena and their effects on RF signal. So this should be on page 59, I think. So yeah, this is on page 59. So basically, the fading channel in both time domain and frequency domain, they change over time and over frequency. And coherent time defines an interval where the fading is considered constant. And then coherent bandwidth is an interval in the frequency domain where fading is considered constant. So if your signal's system bandwidth is smaller than the coherent bandwidth, then the signal can pass through without causing any interference. Otherwise, you'll get frequency selectivity. And also, if your signal's symbol period is smaller than coherent time, then you can pass through the channel without causing any interference. Otherwise, you'll get time selectivity. And so the coherent bandwidth is measured by time difference between multipass, and coherent time is determined by Doppler shift. So this is a little bit confusing because when we analyze what's happening in time domain, we use measurement in frequency domain. And when we analyze what's happening in frequency domain, we use measurement in time domain. But basically, the basic concept of coherence bandwidth and coherent time is the duration over which the fading is considered constant in that domain. And then the key word here for causing coherent bandwidth is multipass for coherent bandwidth and Doppler frequency for coherent time. So in the exam, I will only mark on the keywords. I will only look for the keyword. So try not to write a huge essay on the question. So so here we need to elaborate a little bit further on the definition of coherent time and coherent bandwidth and what caused them. So multipass and Doppler shift, and what do they cause for the signal? So frequency selectivity and time selectivity. So try to do revision based on the questions. So now this question here is you have a 2x2 MIMO scheme, and you use automotive STBC. So you use 2 transmit antennas and 2 time slots. And then for the first time slot, you transmit X1, S2. For the second time slot, you transmit their conjugate, and then also alter the sign of the first one. And then the channel gun, so you have 2 receive antennas as well. So first of all, you need to draw a block diagram for the scheme. Basically, the whole thing is from lecture on the notes on page 128, I think. So STBC transmission is here for 1 receive antenna. And then later on, for the case of using multiple receive antennas, you just stack all the signals together. So this is what you transmitted, and this is a fading channel. So you need to also draw a block diagram here. So this is a case of using 2 transmit antennas and 1 receive antenna here. If you have another receive antenna here, then you just extend this figure and then also write out what you received here. So this fading would become 1, 1 and 2, 1. And then now you have H1, 2 to the second receive antenna, and then H2, 2 And then for channel estimation, you need to estimate four fading guns, and then you do the ML detection. So the block diagram is the first part. The second part is you need to derive decision variables in the receiver and indicate how what's the diversity order. So basically, now you have the fading channel to the first receive antenna, fading channel for the second receive antenna. You follow these steps for one antenna. And then now you have multiple receive antennas. You stack them together. And then in the end, what you get is something like this. So in the end, the diversity order is 2M. So 2 transmit antennas and M receive antennas. In the case of the exam question, you have 2 receive antennas. So the diversity order, overall diversity order is 4. You have 2M replicas of the fading power. So yeah, please make sure that you follow the steps on the slides. During the live lecture, I probably would have time to write it on board, but I don't see much point repeating these steps on my computer now. It's quite difficult to write them down. But anyway, the third question is all the assumptions made in your derivations. So basically, when you transmit 2 symbols over 2 time slots, you need to assume that fading doesn't change over 2 time slots. And then you need to assume that the antennas are synchronized. So you transmit 2 symbols at the same time during 1 time slots. And also, you need to assume that the fading channel is perfectly known as a receiver by channel estimation, so that you can do the ML detection. Another assumption that I didn't mention before is so the diversity here is that the principle of diversity is when you have 2 antennas, then if one fading is in deep fade, the other one might save the signal transmission. So in order to make sure that the 2 fading channels are as different as possible, the 2 antennas should be placed sufficiently far apart so that H1 and H2 will not be the same. So that's a hidden assumption that I didn't mention before. Okay, so that's the first question of the exam paper. And the second question is modulation, the channel modeling. So this is the real part of this quant. You only have one dimension, which is a real part. So basically, this is the same question as before. You need to derive BR based on Q function. So you need to first decide where is the decision boundary. So decision boundary for the first bit is y-axis, and then the decision boundary for the second bit is the scale. And then you need to derive the BR for the first bit and BR for the second bit, and then take average. It's the same as what we did before for the first exam paper. And now you have quant, which has real part and imaginary part. You need to give BR for the whole thing. So real part and imaginary part, they are symmetric. So the BR derivation is the same. The last question here is you need to draw a diagram to illustrate power budget design. So this one is on page 44, I think, of the slides. So this is diagram that you are expected to draw. So basically, the purpose of modeling fading channel is that we can compensate the power loss in advance, so that we make sure that the received signal power is sufficient to support a link. So for example, we have a base station, we have a mobile station, we know the distance. Then the first level is propagation path loss, which causes this much of power loss. So this is the first level of fading, which is propagation path loss. We need to prepare for this much of power loss for the first level. And then the transmit power is reduced to this level. And then the second level, what is the second level of the fading? It is shadowing effect. And how do we model shadowing effect? It's a low normal distribution. So we place a low normal distribution center as a prepared power level, and then we cut off 1 to 2% of the tail, because the Gaussian distribution tail goes to infinite, while we cannot reach infinite signal power. So I have to cut off 1 to 2% of the outage, so that will make sure that 98 to 99% of the case, we provide enough power to support the link, which means we need this much of power for slow fading, for shadowing effect. And then the third level is fast fading. How do we model fast fading? We model it by recent fading or relay fading, depending on if there is a line of sight or if there is no line of sight. So we place another Gaussian distribution and centered as a power prepared when we design the third level of fading. And then we cut off 1 to 2% of the outage. And then in the end, we arrive at a received signal power. So basically, all the path loss, we have path loss for propagation path loss, we have slow fading, we have fast fading, and we need to prepare power for each one of them. They add it together, and when we add them together as total, we have the transmit power, and then we have the receive power here. So for example, normally in a wireless system, we would define how much receive power, minimum receive power that is required. So minimum required receive power. So minimum receive power. And then by calculating the total path loss, we can prepare how much transmit power we need. So that's the last question there. Okay, so that's a third exam paper done. Let's look at the fourth exam paper, which has a more difficult question, I remember. Yes, it has a more difficult question. So I need to emphasize a little bit more on this. Okay, so this is the exam paper for the year of 2017 to 2018. So first of all, describe causes of path loss, diffraction, reflection, scattering, and beamforming, as well as their effect on the direction of propagation radio signals. So they are basically from slides page 14 here. Okay, propagation, reflection, diffraction, scattering, dispersion, and I also asked for the beamforming, which is on page 106. So this is beamforming. So basically, beamforming concentrates signal power to the desired user, to the desired direction, and then minimize the signal power from other directions. Do you have any idea how do we do that? So basically, the signal power fluctuation is due to multipass. So they add together sometimes constructively, sometimes destructively. In order to maximize the power to a desired user or to a desired direction, we impose phase rotations at the transmitter so that the signal, when signal arrives at the desired direction, it is maximized. And when it's arrived at the undesired direction, all the multipaths add together destructively. So the signal power is reduced, it's minimized. Okay, so you need to explain all of this. You can basically for all of this, you don't really need to elaborate more than what is offered from the slides. So you can just use the sentences from the slides to explain all of this. And that is okay to me. The second one is the relevance of minimum Euclidean distance, phase rotations, and peak to average power ratio, and calculate them for 16 quant. I have gone through that before already. So that's that. So C is a more tricky question, but actually I have already offered all the equations you need in here. So you only need to expand based on this. Okay, so let's take a look. So normally when we have BPSK constellation, 1 and -1, we normally assume that the probability of transmitting -1 and transmitting 1, they are equal. They are half chance of transmitting 1 and transmitting -1. However, this question requires that the probability is not the same, and we do not know the probability. We do not know the probability. So what we need to do is that we need to rely on Bayes' law to tell us the probability change. So basically, the probability from transmission is here. So derive expression for the value y that satisfies the relationship here, and use your result to explain why it's optimal. So the relationship that must be satisfied is already given in here. Okay, and this one, let me see how to present this to you as best as possible. This is the most difficult question from these 5 exam papers. So first of all, you need to, this is a conclusion that I give you. So you need to keep this in this form. And using Bayes' law here, we have, how do I show this? Let me write in this area then. So using Bayes' law, we have P, Y. This is what we received. Y hat. And then condition on transmitted X equals +1. And then probability that X equals +1 was transmitted, normalized by the probability that we receive Y. And the relationship requires to require this to equal to the situation of -1. So if you extend P Y equals Y hat, and then X equals -1, and then probability of X equals -1. And then the normalization factor is the same. This is Bayes' law. Okay. It's really difficult to write on here. So here, this is X equals -1, and X equals -1. Okay. So this probability is given to you by this equation. So this probability, if you put X equals +1 here in this equation, then you get sigma 2 pi square root 1 exp minus y hat square divided by 2 sigma square. So this is the first probability. Let's multiply p x equals +1. This should equal to sigma 2 pi square root and then exp minus y plus 1 square hat 2 sigma square and then p x equals -1. Okay, so this is a constant that can be deleted from both sides, and now we have this is what is required to have here from here. And then we want to arrive at here. What do? We take a log to both sides. We take log to both sides. And then in the end, we'll get the decision. So another thing here is P x equals a positive 1. So here, probability of x equals positive 1 plus probability of x equals a negative 1 should be 1, right? Should be 1. So basically, so eventually you'll arrive here because the condition of this is the decision boundary. The decision boundary happens when the transmit signal's probability of transmitting a positive 1 and the transmitting negative 1, they equal. So originally, when it's half-half chance, the decision boundary was 0 here. So if the received signal is on the right hand is positive, then we detect it as a positive 1. But now, because the transmission probability has changed, the decision boundary would have changed as well. What is decision boundary? Decision boundary is happens when you receive signal here lay on the received boundary, where the probability of detecting to -1 and probability of detecting to 1, they are equal to each other. That's why we have the condition relationship here. So in the end, based on this equation, you only have y hat, which is a decision boundary. So in the end, what you get will be y hat equals this. And I have already given you all the necessary tips to arrive here. So in the end, if so for example, the probability, as we said before, if it's half-half chance, then this decision boundary become log 1 minus 0.5 divided by 0.5. This becomes 0. So originally the decision boundary was 0, but now the decision boundary has shifted because the transmit probabilities have changed. So the second question is also a little bit difficult because before what do I have before the Q function is A divided by sigma. But A here actually is the distance between constellation point to the decision boundary. So now for this BR, you need to replace A by 1 minus 1 hat. And another is -1 minus y hat. So you have two Q functions. This is divided by sigma, and then this is This is a Q function. Another is divided by sigma. And this is a Q function. We need to add them together and take average. So basically the decision boundary has changed. So for the Q function, you always need to rate the distance between calculation point to the decision boundary. Okay, I hope that makes sense. It's really difficult to write on my screen. If you still have any further questions, I think it would be easier if you ask your classmates who did attend the class. But by all means, send me an email if it's still not clear to you. But this question is actually the most difficult question from the 5 exam papers. So normally the exam questions wouldn't be that difficult. Right, the last question here is, so now if the demodulator needs to know the noise power and the probability. So how do we know this? So basically, what is the probability of the noise? Where is the received signal model? So I have y equals x plus noise. So the distribution of the noise is 0 mean and the variance of sigma square. And now because the probability has changed, the decision boundary has changed, this would shift. So originally we have a Gaussian distribution here. This would shift the Gaussian distribution. So as a receiver, you still only need to estimate the mean and the variance of the received signal's distribution to see how much is shifted away from the Gaussian noise. So basically, you can you can generate a Gaussian PDF and vary the mean and the variance and see which two values of the mean and the variance is closest to the received data. Okay, so the second question describes 3 types of diversity, and in each case explain why the achievable diversity order is limited. So basically, this is from slides page 97, I think. So basically, you can achieve diversity in different domains. The principle of diversity is to transmit redundancies, to transmit the same symbols in different forms over either 2 time slots, that's time diversity, or 2 frequency bands, that's frequency diversity, and over 2 antennas, that's spatial diversity. And what limits you is that you always have the assumption that fading should be different for these 2 resources. For example, for 2 antennas, fading should be different. So the antennas should be placed as far away as possible. And also, you need synchronization, and you need to have the enough resource for you to achieve your aimed diversity order. So, so in reality, the assumptions may not be met, and you also need channel estimation, perfect channel knowledge as a receiver to perform detection. So all of them can be compromised in reality. So the achievable diversity order might not be the same as how you aimed in the first place. And second question is STBC, you draw a diagram for MISO and then transmit there, and then each time slot decision variable. So this is basically page 124 on slides. So you need to practice this at home and follow these steps on the slides. And then in the end, you have these decision variables. This question is a single receiver antenna, so it's quite easy. And now you have SDMA, where you have 2 users, and then to transmit to a single receiver, so 1 receiver antenna. Let's see. So this is basically on page 113, I think. So yeah, here, all you need to do is to derive equation 68. So I have, let's look at the question again. Sorry, I'm a little bit, this one. Okay, so we have 2 users, each one use a single antenna, and then transmit to a single receiver having 2 antennas. So you have 2 users, and each one have a single antenna. And then at the receiver, you have 2 antennas. You have 2 antennas. So basically, SS1, so the dimension of the input is X1, X2. And then output is Y1, Y2 because you have 2 receiver antennas. So N equals 2, M equals 2. And then you need to do single user decorrelation. And then identify the interference. So this is basically the last page of the slide. You do single user detection first. You apply the conjugate of the feeding channel to the received signal. So if you extend the equation here, you will see that so it will be H. So H here would be 2 by 2. Will be 2 by 2. X would be 2 by 1. Y would be 2 by 1. So when you do decorrelation, when you do single user detection, what you do is once again, you can represent H as H1 for the first column, H2 for the second column. Then it becomes the same as what we did before for the previous, one of the previous exam papers. So you do decorrelating, sorry. So H is H1 for first column, H2 for the second column. It's really difficult to write here. They have H1 conjugate Hermitian transpose and H2 Hermitian transpose. So H1 here. So H1 Hermitian transpose and H1 would give you signal power, and H1, H2 would give you interference. And then you need to do multi-user detection where you do the matrix inverse to completely cancel the effect of fading. So this one we have seen before. So that's the fourth exam paper. No, we only have one left. I think this one, for this one, all the questions are repeated from the previous papers. Let's take a quick look. The first four multi-user access techniques. So in frequency domain, in time domain, in code domain, and in space domain, we have covered that before. So secondly, BPSK, QPSK, this is the same question as we went through before in the first exam paper. So you need to derive BR and also PAPR and minimum phase rotations. So that's already been done. And the path loss model, this is free space path loss. The second one is ground reflection path loss. I have been through that before as well. And the meaning of different parameters, I have been through that as well. And this one, C is probably, let me see, C is probably new. Is it? Oh, C is not new. We have been through that as well. So this is a receive diversity scheme where you transmit a single symbol, and then the receiver receive n replicas, and then you have these signals. So you need to draw a diagram. So basically you have one transmit antenna and then n receive antennas. Okay. And then what you received is h x plus n. So this is n by 1. This is n by 1. This is n by 1. And then the decision variable here can be obtained by the Hermitian transpose of h multiply y. So this is 1 by n. This is n by 1. So you use this directly to detect x, and h Hermitian transpose multiply h would give you the power of all of them added together. So the diversity order is n because you have n copies of the feeding power. That's probably all the questions. Yes, that's all the questions from the past exam papers. I'm sorry, it's really difficult to present this on my screen. So please do discuss, ask your classmates if you have any questions, or you can ask me by email. I hope I can give you good tips without giving you the answer. So I would also suggest you to do revision for the whole course for all of the 3 parts, also part B and part C, based on the exam questions. It would save you a lot of time. Okay, so that's all from me. Good luck and take care.